Good morning, everyone. This is the week 5 of the Mechatronics problem solving session. I will properly start in 1 or 2 minutes. The exam might not be MCQ based because that will be corrected by a person. I cannot guarantee that it's will definitely not be MCQ based, but it'll be corrected by a person. So there's no necessity to make it MCQ based. Okay. So once again, we'll start with a small recap. The lectures 21 and 22 talked about digital circuits, and we'll focus our entire problem session. Okay, 50, a good solid 50% of the problem solving session today on digital circuits. We first started with number bases from binary and octal, decimal and hexadecimal. We'll solve a few questions on converting from binary to octal and the like. Logic gates are also very important, and we'll also be solving a couple of questions on logic gates and how to properly draw them and things like that. And then in lecture 22, we started with this writing Boolean logic as sum of products and products of sum. This has its own small thing, and I will also add a small thing called K-maps to. I'll also add a small thing called K-maps to see how we can write SOPs and POSs easier. The next two parts, sequential logic and memory, will not be we won't solve questions on it, but it was a small important part in the lectures. Lectures 23, 24 and 25 talked about microprocessors and microcontrollers, and most of those are mainly theory, and therefore I will not be solving questions on that. Towards the end, there's a small region about PIC and writing programs, and that I will show how we can write a program for for an ESP32, which is another microcontroller. Are there any specific questions about the lectures of the last week? I guess there aren't. Therefore, I will start with converting between binary, octal, decimal. Give me a second. So I will begin with converting between binary, octal, decimal and hexadecimal. So last week I had shown how to convert from decimal to binary and binary to decimal. We can do the same thing for hexadecimal to octal, and we can do the same thing for decimal to octal. However, it is often much easier to convert everything to binary, and from binary we convert to octal or hexadecimal. So let's take a couple of questions. So I want you to find the. I'll give you a bunch of decimal numbers, and you must find the binary version, and then the octal, and then the hexadecimal. Numbers are yeah. So I'll give you some time to solve this. So for converting 16 to binary, if we use the method we learned last week, we'll get, this is called the short division method. So 16 in a binary is 10000. Yeah, we can do the same method to find the decimal version of 16 in terms of octal. So we can do instead of dividing by 2 in the side, we can divide by 8. So we get 8 divided by 16 is 2, remainder 0. So that means that 16 in octal is 20, or rather 20. 16 in hexadecimal, we can technically do the same thing. However, for converting between decimal and hexadecimal, I do not recommend doing this method, because who knows who knows division by 16 by heart. So we get 1, remainder 0, so it's 10. I am sorry, Harichandran, the 100 and F are wrong, but it's fine to make mistakes. So let's do 63 in base 2. I'll take it to a new page. So we get 1 5 times, 6 times. So the standard way to convert binary to octal will be So we have 1 1 1 1 1 1 in base 2. Since 8 is 2 to the power 3, we can take groups of 3. Each group of 3 corresponds to a particular thing in base 8. So 1 1 1, okay, we can write it out. So the numbers in octal are zeros 0 1 2 3 4 5 6 7. The binary representation of these are 0 0 0 0 0 1 0 1 0 0 1 1 1 0 0 1 0 1 1 1 0 1 1 1. So here we have 1 1 1 1 in the first three digits of 1 1 1. That means in octal, so this in octal 1 1 1 corresponds to 7, 1 1 corresponds to 7 again. So this is 77 in base 8. So in octal we have 7 7. The same logic can be applied for us to solve binary to hexadecimal. But instead of, because hexadecimal is 2 to the power 4, we'll take groups of 4 instead. So okay, I'll write it down. So hexadecimal, the digits in hexadecimal are 0 1 2 3 4 5 6 7 8 9. I'll just write this in. So the digits in hexadecimal are 0 1 2 3 4 5 6 7 8 9 A B C D E F. So the binary representations of these are yeah, you get the point. It'll be a little tiring to write everything off, but you can see how this works, right? I hope this concept made sense. So if you take this thing again, so we have 1 1 1 1 1 1. We take groups of 4. So this in base 16, the first set of 4 will be 0 0 1 1. 0 0 1 1 will be 3. 0 0 1 1. And 1 1 1 1 1, sorry, 1 1 1 1 is F. So 63 will be 3F in hexadecimal. I hope that was clear. Okay, so we'll write this, we'll fill in the table here. Now similarly, I hope has anyone done 125? Hari, did you understand why what he had written is wrong? Okay. Okay, Rakshit says that's the answer. So to be fair, I have not calculated the answer before. I'll be solving it here. So let's see. Oh. Oh my god. Okay, I'm going to calculate 125 using binary addition and subtraction. We know that 125 is 128 minus 3. This is true in any base. I mean, except if, I mean, provided I write all of these in the correct bases. 128 is very easy to find in the powers of 2. 128 and powers of 2 will be, since 128 is 2 to the power 7. Yes, 128 is 2 to the power 7. 128 in base 2 is 1 0 0 0 0 0 0 0. Wait. 1 2 4 8 16 32 64 128. Yeah. And 3 in base 2 is 1 1. We just calculated that. We just found that here. So 125 is 128 minus 3. So we can just subtract these in with normal subtraction rules. There's a lot of carryover, but we've got to do it. So can't forget subtraction. Wait. Okay, yeah. So we can't take 0 from 1, so we do the entire takeover method. So this is 10. Yeah. But we can't, so we have 1 0 minus 1, which is 1. Because in binary 1 0 minus 1 is equal to 1. 1 plus 1 is 1 0 in binary. 1 minus 1 is 0, and then the rest all ones carry down. So 1 1 1 1 1. And that is what Rakshit got. So excellent, good job Rakshit. So we'll write that down. I forgot what I wrote. 1. I hope this didn't go over anyone's head. Like essentially all we did was we did subtraction to find the binary digits. Now the steps for finding octal and hexadecimal will be the same. So let's order these in terms of groups of 3s. So that's 1 0 1 1 1 1 0 0 1. So in octal we'll get, this is 1, this is 7, this is 5. So 125 is 175 in base 8. So since I'm not specifically saying that the number of digits is specified, I'm not saying that in a normal computer, yeah, you have to specify you have to make sure that there are 8 decimal places and so on. But here we're just doing things with numbers, and I just want to emphasize how to get the numbers via normal subtraction and things like that. Like if you're doing this on a computer, then yes, we'll have to put a 0 here so that there are 8 bits. Or maybe if you're using a better CPU, you might have to put 9 zeros, because we have to have 16 bits in the entire thing. But here I'm just showing how to get the binary digits. I mean, no, not binary digits, specifically how to write it in binary. Or were you asking about some other concept? So when you do the thing for hexadecimal, we'll get, if you group by 4s, 0111 is 7. 1101 is, I have to fill in the table. 1101 is D. We can quickly check this. 1101 is 8 plus 4 plus 1, which is 13. And yeah, and 13 is mapped to D, which is D. So hexadecimal, this is 7D. I hope that made sense. Should we spend a little more time on this? We can easily make more questions to solve and check. Okay. So another thing, like, if I had instead said like 9, okay, 9 is easy, but say I instead said 81, then we know 81 is 3 to the power 4, and therefore we can, instead of calculating 81 to binary directly, we can calculate 3 in binary and then do all the multiplications in binary to get it, because multiplication in binary is incredibly easy. So 81 is 3 to the power 4. 3 in binary is 1 1. So 3 to the power 2 is 1 1 multiplied 1 1 multiplied by 1 1. 1 multiplied by 1 is 1. 1 multiplied by 1 is 1. And so we get, so when you add 1 plus 1 is 0. 1 carry over. 1 plus 1 is 0. So we get 3 to power 2 is 1001, which we know is this is 9. We know this is 9 if you filled in this table, but this is just showing how correct we already are. So now 3 to the power 4 is 3 to the power 2 multiplied by 3 to the power 2, and that is very easy to multiply. Most of the terms are 0 anyways, so we are just left with this, and this is very easy to add. 0 1 0 0 0 1. And so if you notice, this is a much faster way to get the binary expansion of 81 than writing the entire long division method. So if you're mathematically fluent enough, arithmetically good enough to find factors on the left or find subtractions and additions on the left, it might make it easier to find the binary representations. And once you have the binary representation, finding octal hexadecimal are just as trivial. So we'll now go and do some. We'll get used to the logic gates. For the important logic gates are AND. I hope the symbols, you have all gone through the symbols and know how each of the symbols are. Oh god, this is a and or not, then there's NAND, not, nor, there's XOR, which is ex- I might be biased, but XOR is objectively the best gate. I mean, it just looks the coolest. If I remember right, it goes something like. Let me just check. Give me a second. Yeah. So one part of the one of the questions which sir had kind of given was like there's a burglar alarm system, and when exactly it should ring and things like that. So I was thinking we can do something of that form, but I didn't want to do a burglar alarm system, and I was not able to generate a fun enough question in time. So I was planning to just like skip that because is there any questions about that burglar alarm system and how each of the parts are modeled? We can go through that entire thing again. So in Sir's class. Like the steps for solving these were yeah, they used AND gates. They used a lot of AND gates for this. It is possible to do this using the other gates also, but you have to think a little to actually solve it in that sense. So in a short time, I'm going to explain another concept called K-maps. Essentially, we will try to solve this using sum of product and product of sum. So the steps they have done is, in my opinion, this is the only way we can actually solve this. Okay, there is one more way to solve this, but it's a little more tedious to write out. So the first step is naturally to define all the Boolean variables. So the question says when active states happen and when it should be disabled and things like that, and they have properly defined it here. And then given this active state, given these variables, we can define a truth table in this format. Oh my god, this is okay. So why did you do this? Okay, so okay, let's just write it out. The active state, an active state with alarm will sound only if the windows and doors are closer. Windows and doors are disturbed. So there are three possible cases, and they decided to so let's spice things up, I guess. Let's solve this in our own method. So there are three cases. Because there are three cases, we should have at least 2 bytes to represent the three cases. Let's say the variable c and d is the 2 bytes required to represent these three cases. If cd is if both of them are 0, then it's case 3, because I feel case 3 is the one which should correlate to 0. If c is 1 and d is 0, it's case 1. And if c is 1 and d is 1, it's case 2. The case of 1 0 1 will not appear, but that's okay. Windows will say W is 0 if windows are not disturbed, and W is 1 if windows are disturbed. M is 0 if there is no motion, and M is 1 if there is motion. So let's consider the first one. There should be an output if the windows are disturbed. So if okay, never mind. We'll first look at case 3. Okay, in case 3 makes sure when the alarm will not make a sound. That means if C, D are 1, if both C and D are 1, I have to do this in using the truth table. Okay, so let's write out the so that's the 16 cases. Output. So case 3 says the alarm will not make a sound if in case 3 we said case 3 is 0 0. That means in all these cases the alarm will not make a sound. In case 1, the alarm will make a sound only if the windows or doors are disturbed. Case 1 was all the cases which look like 1 0. So anything in this region. This is case 1, but it will only sound the alarm if the windows or doors are disturbed. Windows and doors are disturbed, so what happen here. So that's 0 0 1 1. The output is essentially whether or not the signal will ring or not, alarm will sound. Is if it's 0, the alarm will not sound. If it's 1, the alarm will sound. 1 1 is case 2, and this is only when there's motion in the house or if the windows and doors are disturbed. So that is 0 1 1 1. I hope that made sense. They are saying if the windows are disturbed or there's motion in the house. So in this case, in the first case, there's neither any motion in the house or the windows are not disturbed, so it's 0. In this second case, the windows are not disturbed, but there is motion in the house, and because there's motion in the house, there will be an output. Similarly, in option 3, the windows are disturbed, but even though there are no motions in the house, the windows are still disturbed, and therefore we get another output 1. This part does not matter, the middle part, so we can just set all of this to 0. So this is where I feel like it's nice to introduce a product of sum and sum of product notation method, because in what's that thing called, in Boolean algebra, if any of let's say we have 5 variables, a plus b plus c plus d plus d. If any of them are true, this evaluates to true. So instead of looking at we just have to see where these things are true. So here we have a true here, we have a true here, a true here, a true here, a true here, and therefore we just have to add these 5 variables. So this is true. To make this true, we need C to be true, D to be false, W to be true, and M to be false. To make this evaluate to 1, we must do C multiplied by D negation multiplied by W multiplied by M negation. So this term, this term 1 0 1 0. So we want this expression to be 1 at this time at this combination of C, D, W and M. Therefore, the only way that can be done is if we have C multiplied by D negation multiplied by W multiplied by M negation. When I say multiply, it means and, by the way. Okay? So similarly, here we have the next one as C multiplied by D negation multiplied by W multiplied by M. And we have the other we'll include the other 3 also. So that is C multiplied by D into W negation multiplied by M, C D W M negation, C D W M. So if I add these 5 terms, we'll get the output. So the output is C D negation W M negation plus C D negation WM plus CDW negation M plus CDWM negation plus CDWM. We can simplify this a little more. For example, we know that M M plus M bar is equal to 1 always, because either one of these has to be true at all times. So this part can simplify to C D bar W, because the M bar and M will, I'll write it out. And similarly, we can do that here. We can take this and this. So we'll get plus C D M, and the last, this one cannot be paired similarly. So we'll just leave it as C D W M bar. We can draw the thing out, so it will be, if we have 4 inputs. Oh, I can use different colors for different, okay, never mind, I'm not doing that. C D W M multiplication stands for having AND gate, and plus stands for doing the OR gate. So we have to do, we have to do 2 additions. So that will be, the final result is one massive OR with 3 inputs. Okay, so before, when you look at it, you can clearly see that this is a sum of products. We are having 3 products: C D bar W, C D M, C D W M bar. These are definitely products. So this is a sum of product. We can later see product of sum, but product of sum is nicer to see when there are fewer zeros than ones. The output of each thing is an AND. So we have, we have an AND here, an AND here, an AND here. The first one is C D negation W. So we'll take C, I'll take D out, but we need to negate it, so I put the not symbol here and take it in. And then last one was W, so we just pick up the W and put it in. Similarly for all the other terms. So we have CDM. CDM is super easy. C D M, and you can draw this nicely in better softwares. Like this is software just for drawing, so, and therefore it can only draw as well as I can. But so this is the principle behind it. But as you saw, like, this simplification was not very easy. We had to do we had to look very carefully and get the answer. So that is why there's a concept called K-maps. So K-maps essentially help us find the, what's that thing called? K-maps helps us find the combinations of these sums very easily. Essentially, for a K-map, what you start with is, there are 3 variable K-maps and 4 variable K-maps. There are high variable K-maps also, but it gets very difficult to draw. So we'll be having a square. So this is the square. We'll assign CD to the horizontal and WM to the vertical. CD can take the value 0, 0, 0, 1, 1, 1 and 1, 0. Note that I have switched the value here so that just like in the gray code, there's only one bit of difference between each column. WM can likewise be 0, 0, 0, 1, 1, 1 and 1, 0. Now I fill in this table with the values I have. So this might be easier if I just fill in the values which are the ones and put the zeros later. So if CD is 0, 1, so we have 1, 0, 1, 0, 1, 0, 1, 0, 1, 0, 1, 1. And then we have 1, 1, 0, 1, 1, 1, 0, 1, 1, 1, 1, 0, 1, 1, 1, 0 and 1, 1, 1, 1. And then we fill zeros everywhere else. Now, in K-maps, what we try to do is find the largest square or rectangle. So in this case, the largest square and rectangle is this. And then we have this outside. This, if you look carefully, is the D is the D changes but the C is common. That means this will have a value of C. The blue thing will have a value of C, and if you look at it from the other side with the 1, 0 and 1, 1, it will have a value of W. Did I miss a value? Okay. And the black thing, the green one will have a value of C, D, W prime, M. Did it make sense how I found these? Essentially what I had done is, the blue is made out of C, D, W, M plus C, D, W, M bar plus C, D prime, W, M plus C, D prime, W, M prime. Right? So if I was smarter, I would have noticed here itself. We did find those 4 terms. We have C, D prime, W, M prime, C, D prime, W, M, and likewise other two terms here, this and this. So earlier I was only able to notice these. I was only able to notice. I was only able to add this and these two. But here I can add these four to get CW, because we can take here we have M and M prime common, M and M prime common here, and then there's D and D prime common here, and D and D prime common here. So all of this will evaluate as CW. So the final expression is a simpler CW plus CDW prime M. This is equivalent to whatever we found earlier. Though it's not always clear that it's equivalent, but from the laws of Boolean algebra, these are equivalent. I mean, it's very often in Boolean algebra that the results are not intuitive, and I guess this is one of them. Do you want me to repeat how I found the K-map? I guess it made sense. Okay. So if you take another example, for example, say let's take a 3-variable thing with A, B, and C. And let's this time put zeros instead, set which are zeros and which are ones. So let's say this is a 0, and this is a 0, and this is a 0. So we have 3 zeros. Everything else is a 1. Remember, here we had a sum of products. We took a sum of products because there are fewer ones than zeros. Here, naturally, it makes more sense to take a product of sums, because there's only one way to get 0, and that if you get a 0 in any of these, the output is 0. So if I multiply a bunch of things, and if any of them are 0, that means the output is 0. So in this case, we want A to be 0, B to be 0, and C to be 1. If C has to be 1, we'll write this as C. We'll take negation of C. So A plus B plus C negation. This thing will be 0 at this point, and it'll only be 0 at this point. A plus B plus C prime is only 0 at this for this Boolean combination. Similarly, A negation plus B plus C is only 0 for this combination, and likewise A negation plus B negation plus C negation is only 0 for this one. But as you see, in the case of writing this as a product of sums, this is evident. It's a product of sums. We are taking a product of 3 terms, and each of the terms are a set of sums. This is a little harder to properly analyze and say to do what's that thing called, the combinations as we did before. Where did it go? Joining these two and things like that. So but it makes it, this is very easy to do via k-maps. It's very easy to simplify this via k-maps. So when you do, let's take the, because there are three variables, we'll have a three variable k-map which will have two rows and four columns. We'll have AB on the top and C on the side. So that's 0 0 0 1 1 0 1, sorry, 1 1 1 0 0 1. We'll fill in the zeros. 0 0 1, that is this. 1 0 0 1 0 0 1 1 1. Oh no, give me a second. I have accidentally selected a k-map which cannot be reduced, so I will, instead of having this to be 1, we'll take this to be 0. So on, we'll just correct that here. So that, no, that fixes it, and that means 1 0 1 0 0 is not here, 1 0 1 is here. So unfortunately, whenever we take the rectangles, it can only be rectangles of size 2 or 4 and things like that. So here we have this and we have this. Oh, I should fill in the rest of the ones. This is clearly only B changes and A remains the same. So that means, and A is 1. That means, and C is also 1. So this is A plus C. And this one is 1 0 0. So sorry, 0 0 1. And therefore that is A plus B plus C prime. You can see how it was much easier to calculate this than trying to simplify this. In fact, we can verify right now whether this is right. So let us write a massive truth table. A, B, C, 0 0 0 0 0 1 0 1 0 0 1 1 1 0 0 1 0 1 1 1 0 1 1 1. The first term is, okay, we need to calculate A prime, A negative, A not C. Yeah, these are the only two things we need specifically. So this is 1 1 1 1 0 0 0 0 0 1 0 1 0 1 0 1. We need A naught plus C naught. That is 1 1 1 1 0 1 0 1. We need A plus B plus C. A plus B plus not C. So A plus B plus not C is 0 here. A plus, I can't believe I made this mistake. Not C is 1 0 1 0 1 0 1 0. This is 1 1 1 1 1 0 1 0. A plus B plus not C. A plus B plus not C. A plus B plus not C. A plus B. A A A. Yeah. So now if you can multiply not A plus not C and into A plus B plus C, and we get, just we have to multiply these and this, we get 1 0 1 1 1 0 1 0, and that is literally the same thing as the output here. So essentially, product of sums and sums of products are ways we can always concretely write each of the expressions in of given an arbitrary output. Like you just saw how I randomly selected the ones and zeros, and given this arbitrary selection of ones and zeros, I was able to find a product of sums, and we found that this, and we show that this product of sum evaluates the same as the output. We can do the similar truth table analysis or on the sum of products, but that's going to be a lot of addition and multiplication, and I think I showed how to do it. If there are any issues, I can definitely write it out and show you, but I hope that made sense. Okay, so that's the concept of K-maps, and K-maps, I'm repeating this because it's that useful a concept if you're learning about product of sums and sums of products. K-maps are essentially a really simple way to do sums of products and product of sums. As you saw, the map you draw depends on the number of variables. If you had 5 variables, say, then you'll draw a rectangle like, a rectangle like A, B, C, D, E. So that is a rectangle of 8 into 4. And in that big rectangle, you fill in all the zeros and ones, and you select all square regions. But you must make sure the square regions have what's I think called a dimension of a power of 2. So and once you do that, you can easily identify the sums or the products, and there you go. There you have simplified this arbitrary output into sums of products and things of that form. Like, before I go to the programming of the Arduino, I want to ask like a couple of really small questions. Like, for one of the things for binary and decimal, there's this very weird joke, like, why do programmers confuse Christmas and Halloween? It's a very stupid question, and that's because Christmas, we all know, is on 25th December, and Halloween happens on 31st October. And this is such a stupidly weird coincidence, but 25 in decimal is the same as 31 in octal. We can verify that right away. So 25 is 24 plus 1. 24 is 3 multiplied by 2 to the power 8 multiplied by 3. 8 multiplied 3 is 11. 8 is 1 0 0 0. So 24 is 1 1 0 0 0 plus 1. So this is 25. In octal, this would be, we take groups of 3. The first group of 3 is 0 1 1. We know 0 1 1 is 3. And the second group of 3 is this thing, so we get 1. So as a very stupid joke, we have 25th of 25 in decimal as 31 in octal. That's a nice fun one. Actual coincidence. And okay, and then another. Okay, so in addition to doing boolean operators on boolean variables, we can actually do boolean operators on numbers itself, because we know that every number has a binary representation. So we know 16 is 1000 and 63 is 611111. So we can technically do 63 and okay, not 63. We can take 16 and okay, not 16 either, because both of these have too many ones and zeros. Let's take a 4-bit case. So in a 4-bit case, let's take 3, which is 0011, and 7, which is 0111. Okay, let's take 5 instead, which is 01. Oh, okay, we'll take 9, which is 1001. We can take 3 and 9, and that gives us 0001, because we can take and between each of the digits. And is multiplication, right? Yeah, and is multiplication. So when you take and between each of the digits, we get 001, which, so therefore 3 and 9, and is always represented by ampersand. So this is a so we have an entire new operations we can do on numbers. So, and likewise 3 or 9. So this is the way programmers write or. We get 1011, which is 9 plus 2, 11. So this allows us to get the fastest way to check if a number is even or odd. So technically we can take any number, let's say the n, and then AND it with 1. So let's take let's take 3. If you take 3, we have 0011 and 0001, and that will give us 0001. If you take an even number which is equal to 1, if you take an even number, we can let's say 4 0 1 0 0, and then you AND it, you will get 0000. That means you can check any odd number. If you AND it with 1, we will get 1, and if you take any even number and AND it with 1, you get 0. Therefore this is technically the fastest way to check if a number is even or odd, because computers can do boolean operations incredibly quickly. At the same time, because this is the fastest way to find even and odd, the normal way you do check for even and odd, which is using the remainder operator, remainder of 2 in most compilers is translated to is compiled to this, because people who make compilers are very smart, and they know that if you want remainder 2, you're essentially meaning this. So that is just a couple of interesting points I wanted to point out. We'll take a small break now because I need water. So I'll come back in 5 minutes. Coming. Okay, no, not 5 minutes, 3 minutes. Six. Yeah, CS, people who write CS compilers are incredibly smart, and because I work a little bit with programming and stuff, I just appreciate, I sincerely appreciate all these people who write CS compilers because it's wonderfully smart and incredibly cool stuff. Okay, I'll be right back. Yes, I am back. Okay, so one of you had requested that I write the questions before, much before class, and then send you upload the questions. Like I had done it last week. Ha- So I had uploaded the week 4 question. I forgot to upload the week the week 4 PDF, but but I was not able to make questions in time for today because yesterday there was a Mechatronics workshop, and I was in charge helping for the Mechatronics workshop, and I realized that this is one of the code I used in the Mechatronics workshop to show a very simple process. So essentially, we have a microcontroller, and the microcontroller we had is the ESP32. Uh, I guess I can't highlight it. ESP32. So the premise is simple. We have a potentiometer, and we are going to use the potentiometer as an input. The It's a angular potentiometer, and depending on the angle we move the angular potentiometer, the servo, which is a rotary actuator, is rotated to a similar angle. The potentiometer had a range of 270 degrees, like from here to here. We can rotate the potentiometer from this to this range. So it had a range of 270 degrees, and the servo had a max range of 180 degrees. So in the end, it's a very simple code because we just want them to be introduced to the concept of writing code, and not just writing code, understanding how the microcontrollers work and the like. So naturally, before we do anything, so this was quite similar to the one in the last one, in the last class. Sir initially starts with PIC. I am not entirely familiar with PIC, so I didn't want to make a fool of myself by explaining that. But for the snake gate one, he used Arduino. Yeah, he used the AT Mega 32 pin, which has all these. Can't I zoom? Okay, I guess I can't zoom. So it has all the pins and a lot of things. And he has written the code in this manner. So he defined all the servo motors. You might have a question on PIC program. I cannot say that you won't have, but you might. The important thing about PIC program, like if you know the basics of programming, this is not too difficult. But at the same time, if you're and I feel like maybe it's because I'm more comfortable with the C++. I just immediately went to the Arduino example because the Arduino code is written in a more familiar manner for me. So once you know the logic behind programming, many of these steps are kind of intuitive. So what's happening first is we are defining variables, and then you're defining constants and things of that sort, and then you're defining the when you're learning the logic in the end can be learned in any programming language, and the logic is the same almost everywhere. So if I had to write this in the Arduino, it would look very similar. It's just that in different programming languages the syntax is different. So in okay, I didn't need any if statements here, but if I had if statements, it will look kind of similar to what it is here. So it will be exactly like if c equal to 0, but instead of and here I will have the double ampersand which I just showed you earlier. Say if c equal to 0 and d equal to 1, I won't have then in Arduino code. I'll instead open the parenthesis, open the curly brackets, and write the rest of the things. And here we have end if. We don't have end if in the Arduino code. We will just close the brackets. So I thought I'll just explain the basics of programming using these microcontrollers using the Arduino one, and then we'll properly see through look through the PLC code. So in this case, so first we define the variables. Okay, how many of you are familiar with programming? Okay, fine. So in that case, it won't be too painful to see. This is essentially a normal C++ code. We are first defining my servo as a servo because we want to control the servo. If you take specifically this servo we are using is controlled with pulse width modulation. So the setup looked something like this. So we had the microcontroller. We have lots of pins here. I'm not going to draw all the pins. I'll just say the important ones. There's the 3.3 volt pin of the ESP32. There is let's say the pin number 18 and pin number 19 here. We have a and a ground pin. So this is ground. We have a servo. The servo has 3 inputs. So I'll just draw a motor with 3 inputs. And we have a potentiometer. I'll just draw it like that with 3 inputs. We had a 9-volt battery. The ESP32 is connected to the computer because we're coding, so the ESP32 is powered like this. We had what was this supposed to be? Yeah, a battery. Yeah, and we had a L7805, which is a voltage regulator. So time for colors. So I first connected. So we obviously had a breadboard also, but I'm not going to draw the breadboard because that's a little absurd. We first connected the ground, all the grounds. The potentiometer has a ground, and this one. The motor also has a ground, which is the middle pin, and the voltage regulator had a ground in the middle pin also, if I remember correctly. Then we don't want to power the motor using the ESP32 because the ESP32 can only output so much current, and we all know that the maximum speed and rotation of the motor depends on how much current can flow through it. If the motor wants more current, it needs to get it, and it can't get it from the ESP32. So that is why we have this battery to power the motor. However, the battery is 9 volt and the motor only requires 5 volt. That's why we have the voltage regulator. So we give the 9 volt battery to the input of the 9 volt to the voltage regulator, and the output of that goes to the motor. But now we need to control the motor. The controlling the motor comes from the ESP32. So we'll connect that. So here I had taken pin 18 and 19. So this let's say this is 18 and this is 19. So 18 goes to this and 19 goes, okay, I have to. So the potentiometer in the case of ESP32, the input analog values has to be between 0 and 3.3. The potentiometer will give values between 0 and whatever the high voltage is. The high voltage therefore has to be 3.3. So I take the 3.3 and connect it to the high of the potentiometer. Similarly, and now I can connect the input of the output of the potentiometer to the board number 19. So this was the final okay, it's a really ugly circuit diagram, but that's what it is. So what happens is, when we move the potentiometer, the pink wire will relay to the ESP32, and the ESP32 will read that value, and from that value it will calculate what angle the servo should go to. So if it calculates the angle to be 90, it will give a pulse of 90 of width 90 to the pin number 18, and that will be connected to the motor, and the motor will position itself at the orientation 90. So that is what you're supposed to what's supposed to happen. And this is the what's I think called this will be the this is how the hardware this is the hardware side of the entire project. I hope that this section made sense. Naturally, if you're going to do this in real life, you'll have breadboards and use a lot of jumper wires to connect them correctly. But I cannot draw breadboards. Yeah. So this is the hardware point side. Now we have to make sure the ESP32 knows what to do, and this was the code I had written. So pause is an old variable which I forgot to delete before I wrote the code, screenshotted the code. We don't need pause. So servo pin is so and so. Pot stands for the potential pin, and that's 19. I just described that. Serial begin is what is a way that I can get the output of the ESP32 into the computer. This tells you the frequency of how the input and things like that, and this is so that I can easily debug my mistakes. So in case the code is not working as I wanted it to work, I will insert serial dot print line and then put the variable, let's say angle. If I put this inside here, it will. If I put it here, it will. I'll have a feedback on the computer which tells me what the angle is at every time instant, and things like that. So serial is just a way for me to debug. In the actual final code, you technically don't need the serial, but this is just a demonstration. So the servo I was using had a frequency has a time period, has a frequency of 50, and this was from the data sheet of the motor. So in all these cases, which pin you must connect to and what each pins do and what the power input, all of those things are all from the data sheets which you have to Google and get, because all of the motors, like the motor we had used was SG90. The potentiometer doesn't need a data sheet, but it probably has, which will tell it what is the resistance and resistivity of the potentiometer. This likewise the L7805 had a data sheet which tells you what each of the pins does. So from the data sheet I got that the frequency is 50 Hz, and I'm telling the ESP32 that my servo is attached to the servo pin. The 500 and 2500, you don't have to think much about it. Essentially, it's used for finding how to get the correct pulse width in the pulse width modulation. So what in all these codes there are essentially two steps. The first step is, if you look at the code, the first few parts of the code is defining variables and saying defining variables and saying and setting up the thing for the continuous loop. The last part of in this case, the last part contains the loop, and this part will just keep running the whole time. So initially what it does, I'm reading from the potentiometer pin. The potentiometer pin was 19, and I'm doing an analog read from the potentiometer pin. You would think that the analog read will give you a floating point value, giving you the potential. However, I had to read the documentation for this. The documentation said that analog read gives you a value between 0 and 4095. Essentially, it converts 0 to 3.3 volt into a digital input, because because so the potential reading is value from 0 to 4095, and if I want to know what specific voltage is, I can always use ratios and figure out what the voltage is with a little bit of multiplication. So I know the since with this potential reading, potentiometer reading, I can calculate the angle. The angle will be 1.0 multiplied by potential reading divided by 4095 into 180. The math, if you think about it a little bit, the maths kind of makes out. The multiplication by 1.0 is because all of these are integers, and if I just do integer multiplication, it C++ will just give me back an integer. I don't want an integer, I want a float, and therefore I did it like this. And then I do a very simple thing, my server dot write angle. That means I'm saying giving my server dot write will produce the correct pulse width modulation and make the server go to that particular angle. And then I give it a small delay of 150 milliseconds so that it's not running continuously, and that might make the server do things bad. So does this code make sense? Unfortunately, after the workshop, I had to return all the components, so I can't show it here. Yeah, is there any specific questions about it? So, if you read the comments at different places, I'd written this in a manner that the students had to edit the program themselves, and that's why the comments read as follows. Like, read the potentiometer pin. So, initially I'd written in potential reading equal to 0, and they are expected to change it and find what to write here and things like that. So the syntax feeling weird, there's nothing you can do about it. In the end, every programming language is kind of the same, only the syntax changes. Okay, please don't quote me on that. People will people will get really angry if I say things like that. But yeah, many programming languages have its uses in different places. But you just have to get used to the syntax. Like the my server.set period hertz, that's normal C++ function what's that function what's that thing called function syntax. Like if you know a bit of C++, you know objects can have functions associated with them, and therefore this is how it's written. So if we can just look at the other one, and we can clearly see the so if you give me a second, I'll just Okay, so you can kind of see that there are the three cases here. This is the case. This is the case one. This is the case two, and this is the last case. So in the end, even though we found the optimal K map writing product of sums and sums of products, it is often easier to just write out every expression in this format, because if you're writing program, you're not just writing the program for yourself, you're usually writing the program so that it can be debugged later. And it might be someone else debugging and they have no idea how you found that K map in the first place. So how you find that sum of product or product of sum in the first place. And though in most cases it's you who's going to look at the code a couple of days from now and you look and not understand anything. Unfortunately, that's the reality in programming. You will write code and a couple of days later you'll forget everything you've written. The only reason I was able to explain the code here is because I wrote this yesterday. Okay, just kidding. I'll probably be able to explain otherwise also because I've commented it properly. But this code's not commented properly. Okay, this code is commented enough that we can kind of understand. Yeah. So that's the premise. If you look, this is very similar to the. If I had to write this in. Huh. Oh. So this will look like if c equal to 0 and d equal to 1, I will show this on the other computer. Give me a second. So I will. So I hope you can see my screen. Wait. Okay, so if I had to do this one, let's assume it's so I'll just write it in. So what I'm writing is a function alarm that will return a bool, which will tell us when when we should sound the alarm and not. It takes the input C, D, door, window, and motion. You can compare this to the Same thing in the diagram earlier. I do not. Yeah. So essentially, what we will do is, so this will be the syntax in C. Okay, I made a small mistake. If C is equal to false, D is equal to true, true, and if C is equal to 1 and D is equal to, if C equal, yes sir. Oh, it's, can I zoom? Sorry, I didn't. Yeah, is this better? Sorry, I didn't get a notification from the message. Yeah. So the second one was C equal to 1, so this is true, and D equal to this thing. We have, yeah, I can't change that. Okay, doesn't matter. Okay, we have check if the door and window is open. If door or window is equal to true, so equal to true. Or motion is equal to true, then it returns true, else return false, and in every other case you return false. Like if I had written this in C++, there are a little bit of optimizations I can do. Like for example, C is already a boolean, so if I have to say if C is equal to false, that's the same thing as saying not C. Check C is equal to false is the same thing as doing not C. And likewise, D equal to true, that's the same thing as saying D. Because D is only equal to true if D is D. You can check that out yourself. I don't need this because I hope everything's similarly here I can do the same thing. So instead of doing C, I can just do if C, and D. But in the end, it's always easier to just if true slash exist then 1. Yeah, kind of. If I understood what is meant. Yeah, so that is how I'll write this in what's I think called in the Arduino code. So essentially, even though the code looked completely different. Oh, come on. So we have this and Windows Shift S. Give me a second. So even though these look completely different, they're doing the same thing. We can clearly see how all of them are corresponding. I hope that made sense. So in the end, the specific language doesn't really matter. It's just the syntax is slightly different. In C++ and C, you use curly brackets and curly braces to denote if, this beginning of if and end of if. But in the PIC, apparently you use if, else, and if in that specific notation. Give me a second. Yeah, I don't have any immediate material to learn PIC, but the slides had all the equations and all those. So, is there anything specific I must look into now? I hope the concept behind the logic of the program made sense to you, all of you. Okay. Well, so I'll be free to wait for questions for like another 10 minutes. So if we quickly go over what we have done, we have studied a lot. To be fair, this is the longest class I've prepared so far. So we first began with the conversion from decimal to binary, octal, and hexadecimal. We solved a lot of questions on each of these, and I gave you a small hints on how you can do the remainder part in slightly smarter ways. Then we solved a couple of questions, and then we looked at logic gates. Okay, we didn't specifically look at logic gates. We looked more on the logic, and there's not much to know about specific of the NAND gate and NOR gate and things like that. We can have questions on that, like for example, sir can very well give you a question where you have so I can very well give you a question with three variables a, b, c, and then he connects them in absolutely dastardly combinations. Things like this, and then expect you to write what the output is. And then what should I put here? I'll put an XOR gate because it's so cool. And then I'll just put a to top it all. We'll just end with a normal no NOR gate. Like you can be expected to solve questions like this, as that is write what the final output is in terms of A, B, and C. I feel like this is not too painful. It's just tedious to keep writing. So essentially, you just look at each small branch. We have C here, B here. So this is C or B. We have B here. So this is B naught. We have A here. This is A naught. So this is A naught nor B naught. Then we have this is C or B X or A naught nor B. Likewise, this is A and this is C, so this is A and C. And then you have A and C here. And then the output of this is, yeah, you can, the easier way to do this might be to write, you can still write it down. You can write the truth table and find figure out what it simplifies to and things like that. Evaluating truth tables is something which is fundamental, but I don't think we had time to properly evaluate truth tables. I just showed you how we do evaluate truth tables with this example, and after we also properly studied, kind of properly looked into K-maps and how that can be helped in how can that and how that can be used in writing sum of products and product of sums. And that was the main part, and then we concluded with seeing a little bit of programming. Yes, that makes sense. Oh, I guess that made sense. So I guess that's a good recap. I'll wait here for 5 more minutes if there are any more questions. Yeah, Harichandran?
Yes, sir. The out of this one, uh, for just I am asking for the information like this last I am reading this sixth week lessons.
Yeah.
From there, just in the pneumatic system, like pneumatic system was there.
Wait, you said 6th week, right?
Sixth week, I'm reading that I
Okay.
completed the lessons. Just for knowledge information, this pneumatic system, if I am having the pneumatic pressure on the pipe,
Yeah.
okay. So where there, if I am going to measure the leakage pressure, something air pressure leakage,
Yeah.
like a pressure drop,
Yeah.
the with the period of the some more time, like uh, every 1 minute or every 2 minute or every 5 minute, I want to record it.
Yeah.
Based on that, lesson 5 and week 5 and week 6, I am comparatively
Mm.
uh, whether we can use the some sensor like and record with the digital output. We can measure the pressure with the time interval.
Yeah,
Is
it's
it possible?
yeah. That's the there were a couple of. This is week 3, I remember. Okay, not week 3, this is week 2.
Yeah, some sensor.
Yeah.
Yeah,
So in oh, please don't do this to me. Okay. So in week 2, we properly did in the
uh,
floor part. These are different pressures. These are different sensors we had seen. This orifice. The orifice plate was used for pressure readings, and even differential pressure was for pressure readings. So there are sensor. We can have sensors for this very specific task you said. Yes.
yeah. Which is sensor it specifically it will suit for that measure the air pressure drop. Like I'm just linking the lesson 6, week 6 to this week 3.
So it depends on the specific values and things. I
So we like our pressure drop, air pressure drop.
Yeah.
Here the pneumatic proximity can check.
Give me a second. I guess, like, personally, I would have used the. No, I
This logic.
personally won't use the proximity one, because that the prox the that pressure sensor was uh had a boolean output. It didn't give us a specific value. It gave us whether it's true or false, like whether the pressure is high enough or not. It didn't give us a constant pressure reading, if I remember correctly. So this is week 3, week 2. Oh, which was it in it? This is not here.
Is it fluid flow sensors? Does that come in that?
I just checked that one. I remember the sensor which he is saying. I don't remember which slide it was in. Yeah. Why? This one, right?
Yeah,
Yeah.
Yes.
pneumatic.
This one.
Yeah.
This one is only gives us a boolean output, if I remember correctly. Like,
Okay.
no, and this is
So
no,
here when
no, this is a sensor to measure if an object is nearby.
Yeah, it's not the pressure.
Yeah, it doesn't tell us the pressure. It uses pressure to check if an object is nearby.
As like it acts
so
like a proximity sensor.
Yeah.
something like resistance sensor, it can measure that like this.
The-
Uh,
So the best way to do it is to have. I guess one of the best ways to do it is to use the capsule pressure sensor, and that capsule pressure
okay.
sensor essentially, the higher the pressure the capsule expands, the expansion of the capsule can be measured using the strain gauge. So that strain gauge is essentially a resistance sensor. So we have a resistance output given a pressure change.
Okay, so it will measure like pressure. It was converted to the resistance. Then we need to convert the digital to record that the
Yeah,
digital to convert the pressure value.
yeah,
So based on that, this lesson sixth, class 6, the pressure difference P1 to P1 minus P2, we can calculate from that
yeah,
sensor input with the time period.
yes.
Okay.
So essentially, like, in the end, all of it is just like thinking about which what's the correct sensor to use, and then using that.
Oh, yeah,
Okay, so I'll be
yeah,
stopping the recording.
yeah.
Thank you for the class. Thank you for listening to the class.